allá muy interesante de sistemas inteligentes, en donde trabajó todo lo que era tecnología de control en robots móviles a través de visión artificial y planeación de trayectoria. En agosto de 2024 y a la fecha forma parte del laboratorio de Wearable Robotics en la Universidad de Notre Dame como asistente de investigación. Allá fue donde nos conocimos y hubo la oportunidad de que viniera a visitarnos por acá al instituto. Y actualmente está trabajando en un proyecto para estimar y analizar variables en los sockets de las prótesis que tienen que ver con presión y que seguramente ahorita nos va a platicar un poco más acerca de la importancia de todo este proyecto. Entonces, pues démosle un fuerte aplauso a Axel y adelante.
Gracias, gracias. Si tuvieron oportunidad de haber escaneado el código, si no, más adelante voy a tener el mismo código y les voy a dar un tiempo. Let us kick off this presentation with something I'm pretty sure we all understand, and that's football, soccer. I don't know if you knew, but in elite football, the ball has a sensor inside, tracking its position 500 times per second and sharing it to the VAR, or vision-assisted referee, in order to make better decisions or more accurate decisions. Not only that, but we also have sensors on the players and cameras around the field so that we can track the position of each player. And with this sensor, we can even detect tickling around the ball. I'll share you the working principle in a bit. So here, the guy presenting the ball, it's applying some tenure pressure around the ball. And you might think, why do we need so much accuracy in just football? A couple of years ago, we had this situation. I believe the sound is not working. But here they're interviewing the player who was participating in this event. He was from Holland, and the referee marked a fault by Memo Ochoa, and many of us believe that due to this, we didn't make it to the next stage. In the interview, he's saying that, you know what, it actually wasn't a fault. And anyways, if we had this sensor, for example, maybe we could have avoided this mistake by the referee. Now, if we dive a bit in the information of what this sensor is, we find a paragraph of things that say that it's innovative, that it's an advanced suite of sensors, and that they ensure great accuracy, but we don't really get the nitty-gritty details, and that's what I want to share with you with this minor example. To start with, according to the International Vocabulary of Metrology, they should know a thing about sensors and measurements, given that they have the actual meter, the original meter. Their definition of a sensor, it is an element of a system that is directly affected by the measurement. It could not make a lot of sense to you guys right now. Just think of the physical element of a sensor that gets physically affected, for example, deformed, or heat up, or cooled down. In this case, the chip or CPU, as the sources tell that the ball has, it's actually an IMU. And I'm pretty sure that people here in the InIAT are experts in IMUs. And what this specific type, the micro electromechanical system IMU, consists of a fixed frame with a movable proof of mass, which is in the middle. And as the mass moves to one of the sides or walls of the frame, the capacitance increases or decreases. And due to this change of capacitance, we can get acceleration. And this is only 3 degrees of freedom of the IMU that take account for the linear acceleration. We know that the IMU actually has 9 degrees of freedom, but for this example, we only need these 3. And the working principle, really the basics, is this second law of Newton that says that force is equals to mass times acceleration. And given that any pressure or force applied to the ball comes with an acceleration, we can get the force applied to it. It doesn't matter where we applied it. And well, This presentation is not actually about football. It was just to get us started. The next thing that I'll discuss are sensors beyond the soccer field. Specifically, we want to discuss sensors that allow us to get information between the stump or residual limb and the socket, that is the cup that the leg prosthesis comes with. Then I'll share a timeline from very archaic but yet richful methods to get pressure back in the day to e-textiles, which is one of the leading fields in sensing for pressure. Later on, we'll talk about the e-textiles that we've developed at the Wearable Robotics Laboratory. I'll guide you through what can go wrong because there's no perfect sensor. And I have some bonus for you guys. To get soccer outside of this presentation, the sensors allow us to get hidden information because you can't really tell when a player is touching the ball at a specific time frame. So in my research, sensors help us to see hidden information on the socket. And also, just to give you some context, why would someone get an amputation? There's a couple of reasons that pretty englobe the scenario. The number one reason why someone would get their limbs amputated is diabetes or any divascular disease. And this starts with the accumulation of fat on our veins, and that difficults blood flow that then don't allow blood to travel to your extremities, and that's pretty much problematic. You would eventually get one of your limbs amputated for this reason. This accounts for around 82% of the cases. Then we have trauma, and that means it could be an accident, it could be over the war, a bomb. Then the not so common causes, but causes for amputation are cancer, accounting for 1%, and other accounting for also 1%. So pretty much once a subject has an amputation, they usually prescribed a prosthesis to regain support, and so that they can become independent again. A common prosthesis is formed by the socket again, what is in contact with the residual limb, the pylon connecting the socket and the prosthetic foot. And there are other types and more fancy that includes actuators and whatnot, but this is enough for what we need for this presentation. Now, the issue comes with the fact that the residual limb is not constant in its volume, and through changes in volume, we can also get problems in the interface because this socket remains its shape and volume fixed. And just so that we remember, 82% of cases are due to diabetes, and diabetes comes with edema, which means or translates to growth and shrink of volume, and also diabetic neuropathy, and that means that the user loses sensation. And if someone is not able to tell when it's comfortable or where it's not comfortable, they can't really communicate to their prosthetist or the specialist. And that's why we need sensors in this field. As the saying goes, you can't manage what you don't measure. So I know for a fact that some people know German here. So the first paper that I found on this topic is Die Messung der Druckverteilung im Schaft von Prothesen, or in regular English, why bother? Measuring the pressure distribution in the socket of prosthesis, as simple as that. Back to 54. Researchers thought on, well, first of all, in this year, people still wore wooden prosthesis. So that, what I'm trying to say, prosthesis made out of wood. So this was actually innovative. They drilled 100 holes around the prosthetic socket, and then they connected a tube that would apply a pressure, a known pressure, that they would measure by two manometers, a manometer to control big changes in pressure, and a more fine manometer that would control small changes. Their idea behind this was that if you have one of the no balance probes, you want to figure out what's the mass of an object, you could place that object on one side and then place the mass of a known object on the other side. And if they're getting equilibrium or balance, then that value is the value of the mass of the first object. Going back to pressure, this means that if you're applying some known pressure on one of the holes and suddenly the limb lifts, which obviously is not going to happen because they weren't accounting for the anisotropic behavior of skin that pretty much means if you apply pressure in one direction, it deforms in one direction, but also it deforms completely different on a different direction. So the limb was never going to lift, but that's what they thought it would happen. When the pressure applied was less than the pressure felt at the interface between the residual limb and the socket, the limb will remain seated, but when they're kind of similar, the limb would lift a bit. Yet they found some really meaningful contributions to the field. For example, it's very different to have continuous pressures for a long time as to intermittent pressures. You can also increase a lot the pressure if it's only for a small period of time. However, only this much could be harmful for a residual limb. Also, although this was not numerically accurate, the values here were not accurate, they knew that it was different to have, that the pressure was different if the person was standing on one leg, the prosthetic leg, or if they were standing on two legs, or if they were lifting their body with bars. So that's also meaningful. However, the main limitations were that these experiments took almost an hour or more because of all of the changes. They only had 2 probes again, and they needed to change those along all of the 100 holes. And the lift-off error, as I mentioned earlier. Pardon me again for the language. What this table means is that they're comparing standing on one leg, standing on 2 legs, and they first measured the mass of the subject, that's here, and then they try to estimate the mass of the subject by adding up the pressures of all of the 100 holes. And the difference was considerable or not. It depends on your opinion. I believe it was a good result in the end of the day, given the year when it was executed. As time progressed, people discovered transducers, and again, pardon my language, but we need to make a pause. A transducer is usually called a sensor as well, but the difference is that the transducer, if we're specific and we're back to the terms, a transducer is only the element that changes an energy from one source to a different type of energy. Sometimes sensors do that. That's why people name them interchangeably. So this transducer was pretty much a piezoelectric material. And if you have all of those elements and you press them together, that's how you get the transducer that Apple used in his study. It was a bit less than 100 holes, but here the transducer was already mounted. So they didn't need to change the probe from one hole to a different hole. Also, this is more accurate than only applying air and expecting that the interface pressure is going to be the same. So cleaning up a bit this diagram, the strain gauge is only in this side of the transducer. And the working principle is that if you deform however you want the strain gauge, that's going to create a change in resistance that then through a different arrays in electronics, you could actually get a change in voltage. And that change is what you translate to pressure in the end of the day. If it's normal, which is what they did, you only get pressure on one direction, which is good, but it's not enough. And that's why later on, Joan Sanders from the University of Washington, you can note by the date that this was a 25-year of difference between the first experiment and this experiment. Well, they assembled this other array of strain gauges that allowed to also get tangential pressure. So if you're applying pressure on this direction, the strain gauge is going to deform in this direction as well. And that's how you come back to that piece of information, which is really meaningful because, according to the contributions first, they allowed the experiments to be dynamic. The reason being that they included a table with wheels on it, so they could move the whole setup. But also about what I said of having to measure shear as well. In this plot, we're seeing that if the stress applied on the skin, it's uniaxial, meaning only in one direction, meaning normal pressure, the effect is less in so as to the amount of stress causes less strain as if it's biaxial. I don't know if that was clear enough. Pretty much, maybe I should start by explaining what strain is. Strain is the change of length of a material. So you expect changes of length if you're applying pressure on your skin. So by a minimum change of length in skin, you get higher peaks of stress if you have shear and pressure. However, if you only have normal pressure applied, you can withstand more stress. Then the limitations of this work is that they needed to fabricate new sockets for each participant, and that's something we're trying to tackle with the 8 textiles. They were heavy and bulky, adding up to 2 kilograms per socket. And they needed to be perfectly flush. In the first experiment by Appold, they mentioned that this would take half of one day to make sure that all of the sensors were flushed. And well, given that the transducer is something solid, even though you're trying to measure, imagine that this thing is a transducer, even though you're trying to measure the pressure of this area, given that it's solid, and again, you're not controlling how perfect its position is, it could create some pressure already. So in short, you're not completely sure if the pressure that you're reading is accurate because this is already perturbing the environment. And they're susceptible to crosstalk. I'll talk about crosstalk in a bit. After this period of transducer fever, as I call it, because what you'll see is that, I mean, there's plenty of research before this 2022 era, but what I feel like is that all of the researchers were only trying to find new techniques to still use the transducer itself. So I don't see that as new science, more of new technology. Today we have commercially available sensors as the Flexi Force that's based on a resistive working principle. We also have another company called this product is called the F-socket, and the company is TechSkin. So different shapes, different colors, different companies. They're not perfect though. We'll see that in a bit. Other than resistive, there are also capacitive sensors, and they also give you the color map. This is the color map. Pretty much you only get colors on an array. You're not sure of what's the particular value of pressure. So again, resistive, capacitive, and people went wild here because you can even, nowadays, you can even measure pressure by using this transistor that changes the reflection of light that measures the reflection of light as the socket is coming near to where their sensor is. So for short, we have optical sensors as well, and these other kind that are called the fiber Bragg grating sensors. We're not actually covering those. I'm just showing you all of the options. The summary out of this state-of-the-art exercise is that, yeah, there's extensive work on pressure sensors, but there's not best of the best sensor yet. And they're limited to standardization because every researcher comes with a new technique to measure pressure. And there are off-the-shelf options that you could just buy, but they're very expensive, and you don't always get the warranty that you'd like. And that's sad. And finally, again, you need to measure shear, but shear is really at an early stage as compared to normal pressure sensing. If there's no standardization in normal pressure, of course there's not standardization over here. Now moving on to custom e-textiles, but first I want to answer the question, why custom? Again, there's not best of the best. That's not something that we are sure that it's gonna guarantee our experiments. So we need to find out ways to measure pressure with materials that we can get at a lab. And what does the field need before we start assembling parts and designing something? We need minimal modifications to the interface so as to not make the whole setup bulky and heavy. We need it to be comfortable enough so that the participant can continue with their day and do as many activities as they are used to. We need to reduce wiring because that could be a hazard for the participant if they're walking through a narrow area. We also need to customize the whole setup to individual patients. Sensitivity is also important because if you don't have enough sensitivity, then there's a wide range of pressure that your sensor is not going to measure. And again, I don't know if you remember, but I mentioned crosstalk in a couple of slides ago. Right now, we're about to define what crosstalk, hysteresis, and drift are. Imagine you have two sensors, and you're applying a load to one of them. The other one is not touching the first one. It's only adjacent. But yet, if you look at the data, sometimes you can see stuff like this, where the adjacent is actually showing you a measure. And that's garbage. You don't need that. Hysteresis, it's another phenomenon where after applying a load, you're not actually coming back to the path that the sensor is measuring. What I want to say is, ideally, if you're applying a load and then removing the load, you should go back through this line. But this happens a lot. And matter of fact, as extra, hysteresis is also an effect of skin. And drift, which means that there are many variables, and you're only interested in measuring one, in this case, pressure. If you're trying to measure a constant value, sometimes the sensor can drift in time, meaning the measure would increase or decrease unexpectedly. And that's due factors as temperature and others. Also, the age of the sensor matters. Well, here's our roadmap. We've covered the universal language, sensors outside of the soccer field, the timeline. Now it's time to explain what have we done at the World War Robotics and with our collaborators to get the e-textiles, and also what can go wrong with our designs. First, we started, okay, first of all, I'm going to show you two versions. If we were to go back in time, I didn't know there was going to be a version 2. I was hoping it was only that this was going to be the best of the best, but it's not. So resistive, we're measuring changes in resistance. We need a material that is deformable, that if you apply a pressure, then that deformation, it's going to be translated to pressure. But if you remove the load, the material is going to go back to its original shape. So we thought of foam, specifically polyurethane foam. Now, this field is completely unknown to me. I'm trying to explain to you something I don't completely master. This is work of my collaborator, Tian Hao, because he's an expert in materials. So we grab this piece of foam and we dive it in polydilyl dimethylammonium chloride. This is the hardest part of a presentation. It will gain positive electro. So it will gain protons. That's what I'm trying to say. It will get positively charged. And then after this, if you submerge it into a solution that has multi-walled carbon nanotubes, then given that after this, the material is positively charged and the nanotubes are negatively charged, they're going to adhere harder than superglue. And if you repeat this process over and over again, then this is a change, a variable resistance. Because if you connect it to a constant source of current and then to ground, you'll be able to detect changes in resistance, and those changes in resistance is what we use to get pressure. A minor caveat is that this sensor only measures normal pressure. And well, this is the sensor itself. Everything else is just to connect the terminals to voltage or, again, constant current and ground. And just to visualize the working principle better, imagine that you have this simple circuit and you're applying some current. The electrons are going to travel always through the path that has less resistance. But after, now if you have this material and you're compressing it, it's like if you were getting rid of some of the resistance in the chain. Hence, the electrons are going to travel via a path that doesn't have resistance or resistor anymore. So that's what I mean. If you apply pressure, resistance is going to decrease. And through a connection to pressure or linear regression, we can get the values of pressure that we want. In this simplistic example, this is a value of total resistance. So you can check that resistance is actually decreasing. In order to test it with humans, we had to do tests over and over again. In this machine, we had a phantom limb, a limb made out of silicon. And this is an instrument machine. It's applying pressure over and over again. And we measure the response of the sensor, and it was good. As some highlights, the measurable range of this sensor goes from 70 pascals to 4 megapascals. So that's beyond the range that we have interest in. Of course, there's some minor range that we're not covering because of the 70 pascals here, but it's not considerable. I think we can get good conclusions out of this. And this is also important because you want your sensor to react instantly to the load that's being applied. We have a minor caveat here because it takes up to 29 milliseconds. It's still fast though. And it's stable because in this test, we applied a cycle of 10,000 loading, unloading sets. And the response was increasing and decreasing, increasing and decreasing over and over again. We tested with humans. And we got pressure where we were supposed to get pressure. But that's not it. Because, again, this only measures the normal pressure. And there's some spatial uncertainty because the sensors are embedded in a textile. And the textile moves relatively to the residual limb. So being sure that the position of the sensor is set and it won't change matters a lot, because it could be that you put, or for example, this sweater, if you put a cape around the residual limb and then put it inside of the socket, if you've collocated the sensor here, given friction and other relative motion, the sensor could go up or to the side, and that's not, your conclusions won't be accurate. and it's easily detachable. First, we started this experiment with 5 sensors. After the experiment, we found out that 2 of the sensors fell off because of friction. This is how the sensor looks. And again, it's foam and some type of suck. So, and what we used to stick it to the textile was glue. So that's the reason of it being easily detachable. However, we didn't iterate in this design because having shear is way more important than fixing those later details. So we came up with version 2, which is capacitive. In this sensor, we used embroidery. We sewed silver-plated cable through textile, and we came up with a top electrode and 4 bottom electrodes. With the first design, I started saying that we needed something that was compliant, that was deformable. It is the same case here. So for a capacitor, you don't only need electrodes, but you need a dielectric material. In this case, was silicon. So we're going back to chemistry again. Are there any chemical engineers in the room? Okay, good. Because we don't really need to know these names. It's just names. And what matters is the proportion that you're using for each of the elements. These selections of amounts was not arbitrarily, but it was rather a result of optimization. After measuring sensitivity, after measuring the response of the sensor, we selected those that allow us to get the most accurate or the best quality out of the data. So all that's, once you have your dielectric material, all that's left is just to smash it in a sandwich, and that's how you get the sensor. Fabric, gel, fabric. And this is pretty much a capacitor again. One of the sides of the textile is being grounded, meaning it's connected to ground, and the other one is connected to a signal. So now we have a variable capacitor, because according to this formula, permittivity, area of the surface, and distance between these 2 plates, if you smash it, then the distance is decreasing, hence the capacitance is increasing in this case. Now, if I left the presentation here, would be kind of clear for you maybe, but that's a cop-out answer. I'm not telling you the full truth here. In order to measure these changes, this is an analog change of the material. We need an analog to digital converter. And to be specific, that's the FDC. But just think of something that converts the analog measurement to something that we can actually, to a digital value. So what the FDC uses is an LC tank. L for inductor, C for capacitor. If the capacitor was fully charged and you connect it to the inductor, ideally energy would flow over and over again forever, but that doesn't happen because energy dissipates in form of heat. So it would eventually stop, but the cycles are repetitive. Yeah, so we connect it to a known energy supply, and energy starts flowing. What the FDC actually does is measure how long does it take to get energy from the capacitor to the inductor. This is fixed at this point. But if we were to add the sensor, which is a variable capacitor, as load is being applied onto the sensor, capacitance changes, but also the time that it takes to get the energy from one side to the other changes. It could be more time or less time. And that's what the sensor actually measures. With changes of frequency, we get changes of capacitance, and with those, we get changes of pressure. So far, so good, I guess. But I don't think it's fair if I were to left the presentation here, because there are troubles. And also, I want to show you how these signals look like. This is Find Waldo at this point, because we have the man of the hour, Juan, who's part of the InIAT. If you see him around, say him thank you, because he allowed us to go from here to here. I really love this picture because here it looks kind of messy, many cables. It was big and bulky, something that we didn't want at the beginning, but we had to choose because we knew that the sensors work and we needed to do tests. But now, after reducing the size, after improving the energy efficiency and making this record pressure for a complete day, we can actually send a participant home with the setup and measure the whole day. So that's a game changer, big deal. Just so that you have more details, this is a close-up of the motherboard, way bigger than this, way bigger. Nice. Now, I want to show you a demonstration of applying load to the sensor and then measuring it. In this test, I applied first this aluminum bar with this weight. The value doesn't matter at this point. I just want you to have in mind, first we applied a known load, and then we increase the load applied. And that's how it looks, the changes in capacitance. You have a baseline for each of the sensor. I mean, this is only one sensor, but we have 4 channels. So in this experiment, we were only applying normal load. That's why all of the channels are increasing and then settling and then increasing again in the maximum amount of load applied. Then we also tested this sensor with human participants. We placed 3 sensors. These are only labels so that we can identify them. And each of the sensors has a coordinate frame attached to it. Because remember, you need to know where the sensor is in space so that the measurement makes sense. And this is how values of pressure now look like. We translated capacitance to pressure by fitting either a line. This is what my collaborator did on this paper. What I usually like to do is just calibrate the sensors before the experiment, see how the response is. If I see that the response and the load applied are both increasing monotonically, then I would fit a line. But if not, I would feed a polynomial or a quadratic equation to it in order to get pressure. Now, there are minor drawbacks on this sensor. If you were to touch it, then you will start seeing these crazy signals. And this is not usable. We don't want that because here in this range, that data is not worth it. Over here, we can recover some of the information after the parasitic capacitance applied goes away. But we've experienced cases where after really big changes of capacitance, you can go back to English. I forgot to tell you, but you can transmit capacitance with your fingers. That's why you can touch your mobile screens or your Apple Watch or whatnot, or the screen, for example. But anyways, this is pretty much the end of it. I want to thank all of my collaborators. This is Tian Hao. He's defending his PhD today, so it's a beautiful day. This is Professor Shiwon Lee. He's Tian Hao's advisor, and they were designing the sensors, knowing what material to mix with what other material in order to get the responses we wanted. These amazing people we've been working with are prosthetists, and whenever we perform an experiment in south of Indiana, we would reach out to these really, really amazing people. Also, again, Juan, the student who helped us bring the electronics smaller and make them more energetical efficient. We've been collaborating with Dr. Adriana and Dr. Alma, real amazing people to work with. And for the last couple of weeks, we've been recruiting people executing the experiment I told you about to send the participant with the setup home and record data for the whole day. Now, this is us. Professor Bolivar is my doctoral advisor. This is the same QR code that I shared with you at the beginning. So I'm just going to give you a couple of, maybe only 1 minute in case you want to scan it. I'm going to keep going because then I can come back for Q&A. So last and least, we at the Wearable Robotics Laboratory do not focus on making sensors, on designing sensors. We actually try to see problems as an optimization problem. That problem that I told you when you were seeing crazy signals after touching the sensor, if you were only hoping on get meaningful information out of the sensor, you're done. The only thing that's left is just to go home and cry. But with optimization, the question is, what if we could mix and match different pieces of sensor information so that we can get the best quality possible? And that's what we're doing. We're using also a mechanical model to do it. Sorry for not being able to show you more details, but this is work in progress, and we're actually trying to get a paper out of this. So further details to come. Oh, and my advisor will kill me if I didn't say this. It's important to have convex optimization because once you define your problems as convex, it's guaranteed that you'll have a global minimum. And that's if you found out that your problem is convex, then you can solve it in just a matter of seconds or minutes, if so. If the problem is not convex, then we would do something else. We're interested in all sorts of optimization problems. And that's the end of it. Thank you.
Puede ser en español
Sí.
también. No sé, no se presenten. Vamos a cambiar a español para alentar a nuestro público a... Vamos a cambiar a español para alentar a nuestra audiencia a que haga algunas preguntas, así que anímense con toda confianza, Axel. Axel les puede platicar un poquito de su experiencia en investigación. Él está haciendo actualmente su doctorado allá en Notre Dame. Entonces, pues pregúntenle tal vez algo más allá de algo técnico, algo de experiencia. Entonces, anímense. Y si no, yo le voy a preguntar. ¿No? A ver, yo inicio, a ver si se animan. Más allá de lo técnico, creo que has tenido experiencia al trabajar con usuarios y hemos platicado un poquito de eso ahorita que ha estado acá en esta estancia, de las implicaciones que tiene trabajar con usuarios, ¿no? Que a veces cuando lo vemos desde el aspecto de ingeniería, hay muchas cosas que no consideramos cuando hacemos un protocolo clínico, un protocolo que implica trabajar con personas, que implica que hay personas que van a venir y nos van a regalar de su tiempo. Entonces, que nos platiques un poquito cómo has vivido las cosas buenas, malas, las consideraciones que has ido descubriendo justo al intentar aterrizar un proyecto de investigación en usuarios.
Bueno, muy buena pregunta. Yo creo que uno piensa, o al menos a mí me pasó que pensaba que el experimento iba a ser muy fácil, ya había hecho todo lo técnico, ya tenía el sensor trabajando, nada más era citar al paciente y poner mi equipo y prenderlo y pedirle que haga diferentes actividades, pero me fui dando cuenta que desde el primer experimento que es mucho más complicado, es muy necesaria la planeación, mi asesor me dice que tienes que pensar desde que el participante llega, desde que cruza la puerta, porque puedes decir cosas puedes decir cosas que él no debe de saber sobre el experimento. Y eso ya afecta las conclusiones o los resultados. Por ejemplo, si obviamente todo el mundo quiere que su aparato funcione, pero básicamente puedes hacer que el usuario se comporte de cierta manera que no está bien en investigación. Tienes que hacer que su comportamiento sea lo más natural posible. Incluso tú le dices si va a caminar, que adopte la postura como si imaginando que no estuviera en el laboratorio, que a veces es imposible. Pero bueno, regresando a la pregunta, tener un backup, tener extras de todo, es algo muy importante porque nunca sabes cuándo en el momento algún cable se te va a desoldar y entonces no le vas a decir que se espere otras horas ahí al participante. Lo ideal es que te apegues al, a la planeación de tu experimento. Pero muchas veces no es así. Me ha pasado que aun cuando el experimento decía que eran 2 o 3 horas, termino extendiéndome más. Y ahí ya depende de qué tan disponible está el paciente. A ellos son libres de irse en cualquier momento. Entonces yo creo que es muy días antes del experimento, recorrer, hacer pilot studies, que quiere decir imaginarte que no tienes al paciente, pero no sé, te vas a poner los sensores tú y vas a hacer la prueba y si todo sale bien al final, entonces ya puedes hacer el experimento. Mucha administración que uno pensaría que ahorra tiempo si no lo hace, pero en realidad ahorras tiempo cuando lo haces. Entonces, básicamente eso.
Muchas gracias, Axel. ¿Qué más? ¿Alguien más? Curiosidades. A ver, ya te paso el micrófono, por favor, para que quienes están conectados nos puedan también escuchar.
¿Qué tan fácil o difícil fue encontrar pacientes para realizar estos estudios?
Muy difícil. Y sin importar a dónde he preguntado, yo al principio pensé que por ser South Bend, el South Bend es un pueblo muy chiquito y básicamente está ahí por la universidad. La mayoría de gente trabaja o estudia en la universidad. Y yo pensaba, bueno, es el número de gente que vive aquí, por eso no podemos encontrar participantes rápido. Pero luego contactamos gente en Chicago, la Universidad Northwestern, que es muy grande y tiene contacto con el Shirley Ryan Ability Lab, que es un hospital que ayuda a gente con dificultades de movilidad. Ni siquiera ellos. Aquí pensábamos también que íbamos a tener como facilidad, no sé, por chance las reglamentos que nos impone un diferente gobierno, pero no. Aunque haya participantes con prótesis, tienes que encontrar uno que sea mejor para tu experimento. Por ejemplo, en este caso, si el participante es uno del grupo de diabetes y no siente, entonces al participar en este experimento por un día podemos causarle daños porque no está sintiendo lo que le estamos añadiendo a su socket. Y la lista sigue, sigue. Pero básicamente es muy difícil. Muy difícil, pero es bueno tener contactos.
Okay.
Sí, con protecistas, con otros investigadores, redes sociales, por ejemplo, LinkedIn, es muy importante.
Va, gracias.
Primero. Perdón, ¿quiere pasarle el micrófono?
Para que te escuchen.
¿Tienes alguna preferencia de edad para las personas que prueban?
Bueno, en los experimentos normalmente ponemos mayor de edad hasta 65, pero en realidad lo que importa es que sea de un nivel K3 a K4. Los niveles K quiere decir qué tan activo es el paciente. Un número menor quiere decir que no es en realidad, que está o todo el día acostado o que apenas se mueve o pone andadera. Y ya los números altos, que creo que llega hasta K4, K4 ya es casi deportista. K3, pues ya, no sé, alguien joven que camine, que si hace ejercicio que sea recreativo, pero básicamente que pueda mantenerse solo, caminar y hacer las pruebas.
¿Alguien más?
Pero le pasa el micrófono.
Gracias. ¿Cuál es la finalidad del sensor? ¿Es finalmente adaptarlo a una prótesis robótica con movimiento y más motores o necesitan el sensor para algo más?
El sueño ahorita sería tener suficiente información de cómo evoluciona la presión para cierto participante de su muñón.
Sí.
Y en primera instancia, verificar que sí sea la mejor solución su socket. Porque muchas veces la gente utiliza sockets que ya no son buenos para ellos.
Bien.
De mi investigación, en esta etapa, el objetivo final que tengo es poder estimar información donde no tengo sensores. Otra vez volviendo a lo último que dije en la presentación, mezclando la información de diferentes fuentes y teniendo como el espectro total. Ya después, como en siguientes etapas, podría ser compartirle esa data al protecista y el protecista que diga, le ocupo modificar la prótesis, entonces ya hace un nuevo socket y ahora volver a medir presión y comparar esos dos. Pero luego también en el laboratorio tenemos gente que trabaja con prótesis activas, que es prótesis que tienen motores. Y algo que me interesa mucho es poder modificar cómo se mueve la prótesis, porque con control puedes hacer cómo va los actuadores, cómo se van moviendo, la tibia, cómo, en comparación la planta, cómo se mueven, cómo mover la prótesis disminuyendo presión.
Bien. Am, Supongo que esto pues no existía y es algo que ustedes inventaron, pero sí veo que tiene como unas posibilidades infinitas porque lo puedes montar, incluso podrías montar
En zapatos,
un sensor en la plantilla y podrías obtener información del pie que
claro.
sí existe y finalmente analizarlo con el que están haciendo, ¿no?
Claro, 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 sí. Y en cualquier, o sea, como tú lo dices, no solamente
Así
nos
es.
podríamos limitar en sockets, porque hay un investigador muy bueno de el MIT, se llama Hugh Herr, y él en una plática dice que aún no hemos resuelto el problema de presión, porque la ropa te sigue causando marcas, el cinturón te sigue causando, y que aunque tú nada más veas una marca y ya no te pasa nada, a cierta gente es muy dañino que limites el flujo de sangre
Sí,
por pocos momentos. Entonces, sí, las posibilidades son
infinitas.
infinitas.
Muchas gracias.
Gracias, gracias.
Yes. Una duda nada más. No me quedó muy claro dónde precisamente colocaban el sensor. O sea, ¿lo ponen alrededor del socket, del socket o cómo lo...?
Oh, depende
Ok.
del sistema de suspensión que tenga el participante, porque hemos aprendido que, por ejemplo, si es vacío,
Mm,
hay cierto patrón que debemos evitar para que pueda estar adherido al socket.
ok.
Y entonces eso puede hacer que se salga el socket cuando la persona va caminando. Pero básicamente,
Mm,
o entre la pierna residual y las capas que usan, porque utilizan como calcetines, liners
ujú,
y el socket, que estuvieran adheridos al socket. Eso a mí me gusta mucho porque si lo pegas al socket ya no se mueve
mm,
o se mueve mínimo. O la otra es ponerlo en algo textil que ya la persona se pone como calcetín y después el socket.
¿Y ahorita estás evaluando eso con todos esos métodos o estás como enfocándote en uno en específico?
Ya dejamos de lado el sensor resistivo,
Mm,
estamos en el capacitivo y como es el que hasta ahorita nos ha dado mejor información
mm,
y calidad, es lo que estamos utilizando en mis pruebas.
ok.
Yo intento otra vez normalmente adherirlos al socket,
Ujú,
pero si no se puede, pues no voy a gastar nada más el día del participante en no haber
ajá,
hecho nada, se lo pondría debajo.
ok. ¿Y eso no como provoca cambios?
¿De capacitancia?
No tanto de capacitancia, de cómo tiene normalmente el pie dentro del, bueno, el muñón dentro del lugar.
Sí, sí, pues lo ideal sería no añadir nada,
Ok.
porque se ha probado con investigación
Ujú,
que incluso plantillas de 2 milímetros
mm,
tienen un efecto en cómo se mueve el participante.
ok.
Entonces
Bueno.
yo creo que ahí es un trade-off, de una balanza
Mm,
de qué estás dispuesto a hacer para conseguir tu información
mm,
y qué beneficios puede traer eso.
ok, bueno, gracias. ¿Quieres? Sí.
O sea, fuera del lado de, pues que ya comentaste que, por ejemplo, conseguir los participantes para el proyecto, porque sé que eso es una parte muy difícil, ¿cuál dirías que es como lo más complicado que fue en todo tu proyecto?
Estoy pensando. Yo creo que todas las etapas tienen dificultad. Ah, es a veces difícil. Este proyecto tiene parte de diseño, parte química, que es en lo que yo no me meto, pero parte electrónica, parte de algoritmo, porque programamos cómo conseguir la presión y también nuestro modelo. Muchas subdivisiones en las que podrías gastar, ya tengo, en las que podrías gastar mucho tiempo si te enfocas y si básicamente como si te casas en querer resolver ese problema y te olvidas de la imagen grande. Entonces, ese yo creo que es lo más difícil. Sí, estás intentando resolver un problema, pero ¿qué tan necesario es la respuesta a ese problema para tu proyecto? Puede ser, por ejemplo, no sé si te acuerdas que cuando estaba presentando los resistivos, al final dije que también había problema de que el sensor no se adhería mucho. Pudimos haber gastado meses en ver qué otro compuesto usar para que se quedara siempre adherido, pero al final en realidad no íbamos a tener la información de shear o de presión tangencial. Entonces, a veces es necesario, aunque estés estresado, como cortar lo que estás haciendo, intentar ver qué es, o como dibujar un mapa, tal cual en el pizarrón, y ver a dónde quieres llegar. Y eso yo creo que te optimizaría tiempo. El manejo de tiempo es, yo creo, lo más difícil.
Vale, gracias.
Bueno, pues no me queda nada más, no nos queda más que agradecerte de parte de todo el equipo InIAT por tu presentación, Axel, por tu excelente trabajo en estas semanas que has estado acá. Ha sido un gusto tenerte, ha sido un gusto colaborar. Esperemos que esto sea pues el inicio de una gran colaboración contigo, con Edgar, tu asesor, y pues que sea la bandera de arranque para seguir contribuyendo y trabajando juntos a estos problemas que son grandes, son complejos, pero no por eso pues no vamos a intentar resolverlos. Muchísimas gracias. Un aplauso, por favor. En nombre de nuestro director, Jorge González, te doy esta constancia de esta participación en el seminario del instituto.
Gracias. Gracias, Doc.
Otro aplauso. Muchas gracias a todos por su participación. También no me queda más que aprovechar y otra vez a Juan, a nuestro estudiante Juan León, que es Ibero, reconocerle su trabajo, reconocerle su participación, también para hacerles ver que es algo que ustedes pueden hacer si están interesados en salir e ir a aplicar lo que están aprendiendo aquí en la universidad. Se puede, aquí tenemos a la constancia en vivo, entonces por eso aprovechar el mencionarlo, ¿vale? Muchas gracias, Juan. Muchas gracias, Axel. Adri. Gracias a todos los que se conectaron y que estuvieron atentos a nuestro seminario. Los vemos en la siguiente edición del Seminario InIAT. Muchas gracias. Nos vemos a la 1 en el salón.
Mil gracias.
Gracias, Doc. ¿Están conectados?
Sí.